Welcome back. In this session, we are going to start a new chapter on numerical methods for solving differential equations. In this very session, we'll start with ordinary differential equations and methods which are available to deal with them in MATLAB. There are two classes of ordinary differential equations and there are two solvers for them. The first class is the non-stiff solvers and the second class is the stiff solvers. Generally, we will try non-stiff solvers, and if the methods are not capable of performing well on those models and problems, we'll try the stiff solvers. And three of non-stiff solvers available in MATLAB: ODE45, ODE23, and ODE113. And stiff solvers are ODE15S, and S stands for stiff, and ODE23S, ODE23T, and ODE23TB. Generally, ODE45 is our first method to try, and most of the time it's useful and it is capable of solving most of models in ODE form. However, in presence of moderate stiffness or for problems and models with crude tolerances, ODE23 will be better than ODE45, and for models with stringent error tolerances or for models which are computationally expensive to evaluate, ODE113 will be a best choice. And for stiff solvers, if we cannot solve the model with non-stiff solvers, we must try one of stiff solvers, and they are almost cool. However, ODE15S is accurate in comparison with the other three methods, and those methods, ODE23S, T, T, and B, are faster than ODE15S. And if we have some stiff problems, and if we'd like to have a higher accuracy, we must try ODE15S. Okay, let's start with a simple example here. Assume that we have a differential equation in the form of derivative of y equals to minus y plus 2t. And we can write derivative of y in the form of y dot or y prime. They are very familiar notations of denoting derivatives in mathematical literature. The general case of problems and ODEs defined in MATLAB is in the form of y dot equals to a function of time and y. And by time, by t, we mean the independent variable, and y is the dependent variable and output variable. And generally, y is a vector valued function. So, for differential equations with order higher than 1, we must convert it to a system of differential equations of the first order. And for now, this is the first order equation, and it's in the form MATLAB accepts, and we can now define this problem and solve this. Okay, let's go inside MATLAB and let's define the function f, which is a function of t and y, and returns the minus y plus 2 times t. The model is defined, and now let's call the ODE45. This function accepts 3 parameters in its simplest form: the ODE function, which is f here, and a t span, and a vector of initial conditions. Okay, let's pass it f. Then the time span is from 0 to, for example, 2 seconds, 2 units of time, and the initial condition assume that it's 1. And the returning values are t and y. And let's suppress the output by putting a semicolon at the end of expression, and we have the solution here, t and y, and if we plot y versus t, we'll get this. Okay, let's convert this code into an M file. Let's start a new M file and put some clearing stuff here. and let's define if, the final time as 2, and initial condition as 1, and t and y are result of the ODE solution of this f from 0 to final time and this initial condition. And let's add the plot here, and let's add the x label here. The x label is t, and y label here as y, or we can put a t here. And let's turn on the grid, and let's save the program and run it. Okay, we have the output here, and you see now it's the solution of the differential equation. Starts from the provided initial condition. At time 0 we have the value of 1 for the output, and if we change this value, for example, to -1, we can get this, or a negative value, or a positive value. You see the function works well in this, and this is the output of our ODE for 5 function. If we change this value to, for example, to 3, the method which has less accurate than ODE for 5, we'll get this. And you see, if we zoom this, you see that this is less accurate than the ODE 5, and there are some non-smoothness here, and we have a less precise solution. And if we change this to 113, we'll get a similar result. Most of the time ODE for 5 is quite fine and enough to perform numerical solution of ordinary differential equations. Okay, let's start with another example. For example, let's start with Vanderpol oscillator, which is given by a second order differential equation of this form. Let's work with that and solve the problem using MATLAB. Okay, we have the Vanderpol model, which is given by x double dot minus mu 1 minus x squared x dot plus x equals to 0. And mu is a value, and if we change the value of this parameter, the output will change, the behavior of the system will change. And for mu equal to 0, removing this middle term, we'll have the ideal oscillator, which has the output of sinusoidal sine function. And now this is a second order differential equation, and we must convert it to this form: y dot equals to f of t and y. So let's define y as a vector in two-dimensional space. So we have two elements for this. Define y1 as x and y2 as x dot. So the y dot is given by this: y1 dot and y2 dot. y1 dot is equal to x dot, and it's equal to y2, we know. And the y2 dot equals to x double dot, and we must compute the value of this according to original differential equation here. And if we use y1 and y2 instead of x and x dot respectively, we'll get this value as mu times 1 minus y1 squared y2 minus y1. And that's it. We have this system of first order differential equations, which is generally representable by this form. And now we can implement this inside MATLAB. Okay, let's just start with a function named Vanderpol, and this returns the dy here, and it accepts t and y. And let's add some parameters too. And dy is a vector in two-dimensional space, and let's define the first element as y2. We know that the first element of y dot is y2, and the second element is mu times 1 minus y1 squared times y2 minus y1. And that's it. We defined the Vanderpol model, and you see the t is not used explicitly in this model, and we can replace this with a tilde. to remove the warning of MATLAB and change this indicator to green. And it's not needed at all. And remember, in older versions of MATLAB, the tilde notation is not supported. Okay, let's save this and let's start with a new program. I copy and paste this. The model is a function of t and y, and it is output of Vanderpol model with input t, y, and mu, and we set mu equal to 1 here. And using this method, we can provide some parameters from outside of the model into model, and it's a trick to deal with parametric models. Okay, let's set tf to 10, for example, and now the initial condition must have 2 elements, and both of them, if set to 0, then their solution will be 0 in all of the time span. So one of them must be equal to a non-zero value to get a non-zero solution. And that's it. The ODE for 5 will work on this model and we'll have the result. That's an oscillating system, and we can extend the time span here, and that's it. If we add some plot here, we can plot a plot of first state variable versus second state variable, and let's add y1 here and y2 here, and we know that it's a phase plane plot and it shows the trajectory of system in state space. And let's set the axis equal for this plot, and that's it. We have the phase plane plot of this, and we know that this is a limit cycle, which is equivalent to this oscillating behavior of the system. Okay, if we change this value to mu, for example, let's set to 0, we'll get a complete circle here. And if we increase this value, we have this, and if we try other values, we'll get this. And you see, according to this plot, increasing the value of mu will make the model a stiff one. For example, if you change this, you will have this, and you must extend this time span, and that's it. You have this plot. Let's remove this axis equal. Let's comment out that, and you see it's acceptable. However, if we increase this, the program will be slow at evaluating this stiff model. And we can try, for example, 1.5s instead of this to have a faster response and to have a better computational experience. And this is one case we use stiff solvers to deal with stiff problems and have much more speed of computation. Okay, let's return back to 4.5s, and that's it. We have this. Let's turn back to, for example, mu equal to 2, and let's reduce the time, final time, and that's it. We have the output of Vanderpol model here. And now we're going to implement another model. For example, let's search for Lorenz system, and that's Lorenz attractor or Lorenz system. It's a chaotic system of third order. It has 3 state variables and defined as this. And for example, for these values of parameters, sigma, rho, and beta, this model has 3 values. We have this output. Let's simulate this chaotic model and have the response of that. Okay, the model is expressed by this. Let's write down the model here, the Lorenz system, the Lorenz attractor. The model is defined by x dot equals to sigma y minus x, and y dot equals to x rho minus z minus y, and z dot equals to x1 minus beta z. And you see that it is a third order system, and we must rename these variables to, for example, x to y1 and y to y2 and z to y3. And after that, we can express the system as a general form of y dot equals to f of t and y. And for these values, let's write down the values of these parameters: sigma, rho, and beta. I think sigma was, let's see the values. Sigma is 10, rho is 28, and beta is 8/3. And that's it. Let's simulate this model in MATLAB. Let's copy this code and paste it here. And we have sigma equal to 10, rho equal to 28, and beta, rho equal to 28, and beta equal to 8 divided by 3. And let's define the Lorenz system as a function of t and y, which returns these values. The first element is sigma times y2 minus y1, sigma times y2 minus y1, and the second element is y1 times rho minus y3, rho minus y3, let's add some spaces here, minus y2, and finally y1, y2, y1, y2 minus beta y3. And you see we have the Lorenz system here, and we can change this f to Lorenz system, and we must specify a vector for initial value which contains 3 elements. Let's start with 1 0 0, and let's save this, and let's extend the final time of the system. And you know we have 3 state variables, and let's try plot 3 here, and we have this, and let's add the z label here. We can change this to x, y, and z, and also we can turn on the legend as x, y, and z. And that's it. Let's run the program, and you see we have the output of Lorenz attractor, Lorenz system here, and if you rotate this, this is the shape of Lorenz attractor, which is actually a set of infinite unstable limit cycles, and that's why the system is called chaotic. And if you zoom here to see the value of states, you can see here this is the values of states in different times. And if you extend the time span, you'll get a more comprehensive plot of the states. Okay, we implemented the Lorenz system and used the ODE45 to simulate it. However, if you use this method and you cannot get the acceptable solution of the ODE, you may try other non-stiff methods, ODE23 and ODE113, and if all of them are not capable of performing well on the model, then you may infer that the model is stiff, and you may try with 4 stiff solvers. Okay, that's it. We finished with a numerical solution of ordinary differential equations in MATLAB.